So today we have first to introduce that wonderful day, Pedro, that will tell us a bit about the role of asymmetric radiation field in shaping protoplanetary disk chemistry and dynamic in stellar binary systems.
Yep. Thank you for the introduction. By the way, this is a very long title just for talk about phantom2025 in binaries. So this is the short title I want to introduce you. So let's start. I give you a brief physics problem that we try to solve with this implementation. Well, we know that the protoplanetary disks are composed by dust and gas mixture, but these mixture are not in the same temperature one each other. So temperature, for instance, is dust temperature is lower, has lower values in the surface layer than gas, and the only region when dust and gas has roughly the same temperature is in the midplane. So this is very important to sustain the dynamical structure of the vertical structure of this protoplanetary disk. Another important aspect to consider in this asymmetrically temperature map is, well, in different surface layers you can observe different reactions. So when in the surface of the protoplanetary disk happens different reaction that happens in the midplane due to the temperature and penetration of these photons and other source of energy like cosmic rays, for instance. So for that reason, modeling the temperature in your protoplanetary disk, in your whatever you are working in disk, is very, very important to capture these kind of effects in basically the thermal stratification. So for that reason, phantom and mcfost can work together. So the idea is to, it's just outside. The idea is to use the hydrodynamics of phantom to compute all this motion equation and calling mcfost in order to compute the radiative transfer and obtain the temperature that phantom can use to compute the final state of the particles. So far there is a couple of works that have implemented this kind of implementation. So the first of them was Christophe in this modeling, this kinematic signature. Then Beck used it in rocky shadows to model the effects of this misaligned inner warp disk casting shadows in the circumbinary disk. And then two works in FAU Orionis by Elizabeth, this one and this one. And finally, the latest one, the work by Sal about the comparison between a radiative disk and a beta cooling disk prescription. So unfortunately, I am not sure about that. If you want to know about how the code works, the both codes, you have to read them because there is no official documentation about how this implementation works. So you have two ways to know about how this implementation works. Read these methods in these papers, all talk with Christophe and Daniel in consequence. So this is an overview about how the code works, basically. You see here the classic phantom loop. So you start with an isothermal disk, and you use phantom to compute an isothermal temperature profile to solve the equation motions and produce snapshots. That is your result. But now, if you use mcfost to compute the temperature, well, in every time step, you call mcfost. mcfost needs the stellar spectra and dust distribution in order to compute this radiation map in the space. Then, with that information, compute the temperature map and pass it to phantom to compute the equation of motion, and then you have this greater loop just to this one. So this is the overall how they code work together. And for everyone who don't know, well, mcfost work with sending photon package from the sources, in this case it's the star, and use the SPH particles as a reference to build a Born mesh, and then every particle does interact with the particles. Every photons interact with the Born mesh, and every cell will have a different temperature depending on the local condition of a disk and the energy of the photons. And so I use that one to model this protoplanetary disk. Actually, it's a circumstellar disk in a binary system, in which I use a mass of the disk of 10 to the minus 3 solar masses, I initialized this simulation with a fixed value of dust-to-gas ratio 0.01, but I am trying with two prescriptions. First of them is to assume that the dust-to-gas ratio is constant in every time of the simulation. That means that dust is perfectly coupled to gas. But I also use the one fluid dust prescription in order to see if the dynamics of the dust, that means the settling, can affect this radiation field in the disk. So this is the value for the central stars and the size for the disk. I'm using just a standard value, just sun-like stars. And I am setting a binary. Well, I set two binaries. One of them is a binary 1, that is a twin binary system. Both stars are the same. And the secondary binary 2, is 0.5 solar masses with a corresponding luminosity of 0.036 solar luminosity. That means I am assuming that one I am in the main sequence regime. And finally, the parameters of the stars is the semi-Meraxius 50, eccentricity 0.5, and I try with two inclinations: coplanar 0 inclination and inclined 30 degrees. And these parameters give me a period of 250 years roughly for the binary. And another important thing I need to consider is I define this new quantity, comma, that divides the disk in two sides, one side close to the secondary and the other one part of the opposite side of the disk, that will be useful to compare the effects of this radiation with the companion. So there's the results. You can see here the vertical structure of the disk, and this is the radial structure in terms of the super density. And I try here three types of simulations. The first one, the green line, is the classical thermal prescription, and the blue one is one source. That means that I am only considering the radiation that comes from the central star and avoiding the radiation from the secondary. And the third one is in magenta, is when I consider the radiation of two kind of sources in order to compare the effects of the secondary over the circumstellar disk. So you can see this, the coplanar and inclined configuration. So the first thing that we can observe with this kind of implementation is that now, if you start, because I forced to start by constructing the stimulation start in that point, they drop to another value of the h/r, because now the vertical structure can freely evolve in the time according to the local optical properties of the disk, in order to obviously as well in terms of the radiation of the star. So then you can see this effect here, this new value for this part of the disk, but also in this part of the disk, you can observe the very puffed up in this part due to the secondary. In this case, you can observe that this is the disk without the radiation of the secondary. But now, if you consider the radiation of the secondary, you are observing an increase in that value that is also observable in this site. Because when you are in the inclined configuration, yes, you can observe this secondary radiation. But if you are in inclined configuration, your secondary stars can irradiate phase. There's a vertical component that can easily penetrate the midplane to the disk and hit them easily than in the coplanar configuration, because all the radiation is in the plane of the disk, so there is more extinction there. And another important effect in order to consider, because the mcfost interacts with the disk, because there are some dust in the disk, so to create this extinction. So in this case, I compare these two prescriptions. So in this case, the blue is the classical dust-to-gas ratio constant, and the magenta is the one you consider the one fluid simulation. In this case, dust settle to the midplane freely, is in modeling with this kind of prescription, and this increase the optical thick in the disk along the disk plane, and the result is that in overall your disk is colder than when you fix the dust-to-gas ratio, and this is the relevance of the inclination of the secondary, because in this case there is no difference between two models, because now in this part where the radiation is dominated by the secondary, the radiation comes from a vertical component, so the dust sledding the dust settling in the plane is not affect at all this the structure in this particular side region of the disk. Another important aspect to this implementation is that now you can compute some temperatures. In particular, you can estimate some regions when you expect to find these snow lines. So you know the snow line is a region when happens the transition between state between gas and dust for certain molecules. So you can see here different molecules, and you can see here the corresponding observable in a disk. So but these values that are given there are very strong depending on the local disk dust and gas conditions. So in my work, I am consider this only 5 species: the water, CO2, CO, N2, and NH3. And with these values, that this is the vibrational frequency and the disruption energy, are computed by laboratory. And there is a lot of sources that give different values for that, but can give us an idea about what is the temperature of which particles can freeze out. So I am using that species in order to trace the change in these snow lines. So you can see here the label for this line. I hope so. But you can see here the function, the dependence of these isothermal lines as the binary phase in different cases. This is for binary 1 when the 2 stars are equals. This is binary 2 when the secondary star is smaller than the primary. So you can see here how this temperature change along time in the time according to this binary phase. So this is very useful. But now, if you want to make some values, well, in this case, I am just tracing 3 different particles at 3 different radius and see what happened along 2 binary orbits. So the pericenter is marked with this gray line here. So you can see a modulation in the temperature. So they are increased the temperature when the companion pass close to the disk. And this is a periodic behavior that you can 3 minutes. And you can observe here. So this is a very strong implication for the freezing out and sublimation cycles for the particles. So another interesting thing that you can do with this is to try to mimic outburst stars. So you know that some kind of stars can experience outburst events in their lives. So the most famous is Orionis and the XOR types. So the mechanism behind that outburst could be different. So first of them, you can obtain magnetic rotational instability. That means due to the high magnetic fields of the stars, can accrete a great portion of the inner region of the disk. So you create that material and you produce an outburst. You can see here the corresponding value for luminosity and accretion. The other possibility is the clump accretion. So you have a fragmented disk. You can create some clumps of material in the disk that can be accreted by the primary stars, and then you create an outburst. And the classical one that Nico told you about this is about the flypaths on Tuesday. That means that just the companion pass through the disk and hit and accrete material and create an outburst. So the main consequence of that kind of outburst is that you can move the snow line from the quiescent position to a different position. You are displaced that kind of snow line because you are hitting the disk. So with that implementation, I can artificially mimic that kind of outburst in which I manually alter the luminosity when the companion pass in the pericenter, and then create an increase in the luminosity. So you can see here for the binary 2 in the coplanar and inclined case. And with this kind of result, I trace the instantaneous behavior of the disk. So the first of them is that in the coplanar, you can observe a great increase in the vertical structure just in one side because it's in the coplanar. But now, if we now observe the inclined case, this increase in the vertical structure is also in the opposite side. So this is the very important of the inclination when you are irradiating a circumstellar disk. And then if we now compute the behavior of these isothermal lines, well, you can observe here this pre-outburst and post instantaneously after the outburst. And you can see here that your disk is practically heat, obviously. You move the isothermal lines, the snow lines, touching the circumstellar disk from the secondary. And you can see also observe the difference between equiplanar and inclined configurations. In this case, you can observe that there's a portion that the disk remains below 50 degrees. But now, if you with the same luminosity increment, you can practically heat your wall disk by temperatures above 50 Kelvin. So the relevance of inclination when you are irradiating your disk is really, really important. So yeah, so to finish. I think we are in the time, but yeah, with this kind of implementation, we can model a 3D highly asymmetric radiation field in order to compute the temperature map, and you compute the corresponding dynamical behavior. It's useful to trace some chemical behaviors like the snowline changes, and now your temperature is no more a power law. So it's more realistic, but it's not enough because we are assuming that it's a local thermal equilibrium. So despite this a good method to observe this kind of physics, it's not perfect so far, but in some future, we hope that we can obtain this different way to compute the temperature in order to get more accurate. So that's all. So thank you.
Nice talk. When the outburst stops, how fast does it take for the dust and the gas to go back to the previous conditions? I mean, is the chemical evolution faster than the dynamical evolution?
Yes, this is a good question, because this year I released a paper that traced that. Because there is a source, I don't remember well, I can send you after, but when you hit the disk, the corresponding change in the chemistry in the disk is instantaneously when you hit the disk. But now when you turn off, in some words, your stars, some chemical elements remains in the disk despite that the temperature is not enough. So this is the delay after the heating. So the heating is instantaneously, but the cooling to the disk presents some kind of delay. So this kind of stuff I cannot model here because I am not modeling chemical species, but that happened in the observationally.
I do have one.
Yes.
So there is dust in your simulation, if I'm right.
Yes, one type simulation.
But I'm not sure exactly. Like, have you used multiple species, a single grain species?
Sorry. Yes, I forgot to mention. I am using just 3 grain species in the regime of Stokes less than 1, because I'm using the 1 prescription, so I cannot pass 1. But I am using 3 species, 1 close to the micrometer, 1 close to the millimeter, and 1 close to centimeter, I think, in order to don't overpass the Stokes numbers. But yes, I am using 3.
Hi Pedro, thanks for the talk. So I have a question, but does phantom plus mcfost work with 2 fluid?
Yes, I think it is able to work with 2 fluid. I would like to explain how it works, but there is no way to explain. But in my opinion, I think that in order to yes, so I think this is my thinking. When you are here, the Bourne mesh here is built using the SPH gas particle position. In 1 fluid is the same, but I think when you use 2 fluids, this Bourne mesh is based on the dust SPH particles, I think.
Well, there's an option actually.
I don't know, so in my thinking.
It's built on the gas by default, but there is an option to build the mesh on the dust.
Okay, there is an option there.
Thanks.
It's interpreting. It's
Or just to comment on that question as well. So the mcfost obviously needs the full grain size distribution. So it will try to reconstruct whatever's missing in there. We do have some documentation on this actually, which is if you have like one grain species that's large, mcfost makes like MRN distribution and then tries to like extrapolate your one large grain. If you obviously provide enough grain bins, it can just kind of interpolate between them. Or it can just forget about the large grain and just use, because for radiation, you know,